So we started with chapter 5, which is on forces. As we said before, this is a mechanics course. And when we study mechanics, we have two branches of interest. These are the kinematics and the dynamics. Kinematics, we said at the beginning of this course, it is basically the study of the characteristics or the properties of motion. So we are interested in a particular motion. We like to characterize it, we describe it. And later we worry about its causes and how we can make this kind of motion. And this is basically the branch of dynamics. In kinematics, we studied quantities such as velocity, time, displacement, acceleration, and we measured these and gave some time equations, and we gave some special types of motion such as circular motion, projectile motion, free fall, etc. Now, we would like to see how this motion can be made. Namely, to cause motion, you need to make a force, and different forces will have different impact on the motion of an object. Certain forces would give us circular motion, certain forces will give us accelerated motion, and certain forces will not give us motion at all. So what we will do is we will study the effect of these forces on motion by studying Newton's laws. So we'll start with a definition of forces and mass because it's the fundamental quantity in mechanics. If we don't have a mass or an object with a non-zero mass, we really cannot study any kinematic or dynamic properties. Next, we will proceed to define Newton's laws of motion and some examples of forces that can exist in nature. And finally, we will apply Newton's law and see how we can check the type of motion that we will get from these forces. So what is a force? From high school, you took this simple definition of forces to be a push or a pull on a certain object. And this push or pull can occur either through contact. So I pull a rope by holding it by my hand and pulling it, or over a distance where you are not really touching an object, such as when you release a ball in air and this object falls down due to gravity of Earth. So Earth exerts a gravitational pull without even touching an object. So here I have the case where we are pulling a card by contact with a rope. So we have contact here. Here we do not. But in both cases, forces can be exerted either way. A person here is kicking a ball, he's exerting a muscular force, and it needs contact. He touched this ball and then kicked it. A person here is pulling a spring, and obviously there's some kind of contact occurring. In fact, most forces are contact forces. The ones which act from a distance and do not need contact are three forces only, actually. The gravitational forces, the electric forces and the magnetic forces. A magnet can pull certain metals without being in contact with them, so it can act over a distance. Electric forces, this is the force between negative and positive charged objects. So these are electric forces. The positive attracts the negative, and like charges repel. These also act from a distance. So these three are basically the ones that act over a distance. So these can be like categorized into two types of forces. Now, a more scientific definition of forces is to say it is an interaction between two objects. As you can see, it always involves two objects. I have here in our first example, Earth is basically our first object, Earth, and our second object is this falling ball. So two objects interacting, Earth and the ball. Here, this person and the football as well. And here I have this girl and the cart. These are the two interacting objects. The girl is exerting a pulling force on the cart. And similarly here, so it's always two objects interacting, and the result is a force. And as we know, a force has different directions. Earth always pulls downwards. A muscular force can be exerted in any direction according to the motion you're interested in. The pulling of a rope will always be along the length of the rope itself. So we have different directions associated with a force, which means it is a vector quantity and its unit is measured in newtons, following Isaac Newton, who characterized forces thoroughly and mathematically. So this is our SI unit. Now, before we proceed to analyze forces more, I will just remind you of the definition of mass, because it's our fundamental property in mechanics. If we don't have a massive object, a certain object with a given mass, we cannot study any forces acting on it. So the mass is basically the amount of matter that exists in an object. If I have certain number of atoms, these have different masses. The object itself will have a particular mass according to the amount of atoms that we have in it. If you remove atoms from an object, then you're removing some mass, its mass will decrease. So, and remember, by the way, I wrote here a nice formula for the mass, which reflects the amount of matter clearly. So I wrote the formula for the number of moles, which is the mass over the molar mass, and this is equal to the number of atoms over Avogadro's number as well. If you rearrange for the mass, you get this formula, which is the number of atoms times the molar mass of the atom over Avogadro's number. Notice how the molar mass and Avogadro's number, these are constants. So the mass is basically a constant multiplied by the number of atoms. So it's related to the amount of matter that exists in a certain object. Its unit is kilograms, and as you can see, the mass is a scalar. It doesn't have a direction. It's the amount of atoms. These don't really have a direction. So the mass is gonna be really our object, which feels some forces. When we study forces, one mass can have multiple forces acting on it. We have studied this particular case where I have an object tied to three ropes, and we are exerting different forces on it across the three ropes. We're making different pulling forces. Now, when I have multiple forces acting on an object, I can study the net force, or the vector sum of all of the forces on an object. I can study the sum of all of these forces together. To sum all of these forces, I remind you of what we did when we studied vectors. We drew the vectors, either starting from the same point as I did here. So I drew F1 and F2 and later F3, and then I draw the sum by using the parallelogram method. Or we can use the tip to tail method. Notice how here I drew F1. I just copied F1 from here. Here it is. And F2, I copied it such that its tail starts at the tip of F1. Here it is. Now I'll just use the tip to tail method to obtain the sum of these two vectors. Let me show you. When you sum F1 and F2, you will get a vector here. This is F1 plus F2. And then I will proceed to add F3 because I have three forces to add. I started with the first two, found their sum, here it is. And now the tip of this sum with the tail of F3 is here. So the sum of F1 plus F2 and F3 can be drawn also by the tip to tail method. I'll connect the tail here to the tip here, and you will get F net. This is the sum of all of the three forces. And now I can draw the ball to be feeling just one force, which is F net, which I found its length and direction here. I'll just draw it. So basically the ball feels this net force, this total force, okay? So when we have multiple forces, we can add these forces by using the method of summation of vectors. Now here I added them graphically, but remember in vectors we also added by x and y components. We're going to be doing that as well. Now what you noticed here as well is I drew these forces acting on an object. This diagram where I draw the object with the forces acting on it is called a force diagram. It just shows the different forces acting on an object. An example is also this sketch of a book on a table. I just simply ask you draw the force diagram of this book, and then you will draw the forces acting on the book. We're going to define different forces later on. Here I drew the weight and the normal force exerted by the table. One thing we notice is this object is not moving, so I know that these forces must be canceling out. So if you look at the options I wrote here, select the correct F net for the above figure. If you add these two forces, by vector addition, we're going to subtract these because they have opposite directions. So they cancel out because they have same length. You subtract them, just get a zero net force. Thus, these two vectors cancel out. Here, F net is zero. So actually, the book is feeling no net force at all. So I have here some more examples of force diagrams. And as you can see, we have the same object A feeling different forces according to different scenarios it is in. I'll start with the simplest case where object A is falling in air. So maybe it's a good idea to write this here as a note. A is falling in air, and thus the only force it will feel is the pull of gravity, pulling it downward. I want you to notice if you have a bigger mass, another object B with a bigger mass, then gravity will pull more on it. Gravity depends on the mass of the object. You can see how the mass starts to show up as we work more and more with forces. If object A is on a table, it doesn't really fall down. This is because the table cancels out the weight force. The weight which is downward is going to be cancelled out by a force by the table called the normal force, which is upwards. We're going to be talking more thoroughly about these forces when they are exerted and their directions in the future slides. But for now, what matters to me is that you can see that every object can be characterized by a force diagram, which is a figure in which the object can be represented as a point or as it is. Here I left A as it is and I drew the force on it. Here I represented object A by a point and drew the forces on it. Representing the object as a point makes things easier because you can directly add the forces acting on the object because they will all be starting from the same point. So use the parallelogram method directly and more easily. And we draw the forces acting on this object as, as vectors. You can see here I have another scenario where object A is hanging from a rope. So there will be a weight force acting on object A, and the rope will be holding A from falling due to the weight force. So there's a force exerted by the rope. I name this a tension force. And finally, I have object A hanging from a rope and also in contact with the floor. So in this case, both the floor and the rope will exert upward forces to prevent object A from falling down due to gravity. So I'll have the downward effect of gravity and an upward tension by the rope and an upward normal force exerted by the floor. So you can see here I have drawn different force diagrams for different scenarios. Basically, I went through simple steps to make these drawings. I'll start by identifying all the forces acting on the object. So when the object was just in air, I knew I simply had just the weight force. When the object was on the floor, I knew I have also a force from the floor. So I identify the forces, and then I sketch the object, draw the vectors representing each force. And when I draw the forces acting on this object, I am careful about something in particular. One, I will draw the object as a point, and then I'll place all of the forces to start from the object. So their tails are on this point. And then we make sure the vector directions are and magnitudes reflect the length or the size of the force. So here, for example, the weight force is going to cancel out with these two forces, the tension and the normal. So I drew the tension and the normal such that their length adds up to be equal to the length of the weight force. So when you draw, the length of the vector should reflect the size of the force, and the direction of the vector should reflect the direction of the force. So I have drawn here for the first example, objects A and B. These are in air, so the only forces acting on them are the gravity of Earth. Because object B is heavier, then it will feel more gravity force. So I will draw a longer vector for it than the vector acting on object A. And gravity always pulls down, so I draw these two vectors to be pointing downwards. So in a force diagram, I'll represent the object as a point. I'll identify the forces I have according to the scenario I'm studying, and I will draw these forces such that the direction of the vector reflects the direction of the force, and the length of the vector reflects the length of the force. You can see here, for example, how I drew on purpose the tension force to have the same length as the weight force, because these two should be equal to each other for object A to stay like hanging, not moving, right? So let's check a couple of small examples. I have here a block is pulled along a rough level surface at a constant speed by the force P. I have a force P here, which is pulling a block. The figure shows the free body diagram for the block. Fn represents the normal force, and F represents a friction force. We're going to be talking more in details about these different forces and when we see them. The question is, what is the magnitude of the normal force? So one thing I know is the block is moving along the level surface. It's moving along the horizontal. So my first comment is block is moving along the horizontal, which means that along the vertical, there should be no motion. And if I don't want to have any motion, then the forces must cancel out. Forces along the vertical must cancel out. If I have a net force along the vertical, then the object must move along the vertical. which is not the case here. So if the forces along the vertical cancel out, this means Fn and mg, these are the ones I have along the vertical direction. These must cancel out, which means these should be equal to each other in terms of length. And they should be opposite in direction to cancel out. So if I'm interested in the magnitude of Fn, this should be equal to mg. This is answer D. Another example, two forces act on a hockey puck. For which orientation of the forces will the puck acquire an acceleration with the largest magnitude? So I have same forces applied in different directions. So here I'm really looking for the largest net force. We'll talk later about the relationship between acceleration and net force, but I want the largest net force in this question. If you look at Fnet will be the sum of the two forces in each case, right? If you add these up, you will notice that Fnet will have really different lengths according to different scenarios. In particular, I know D will have the smallest Fnet because here the forces cancel out, right? We are subtracting them rather than adding them. But I also know that when the forces are along same direction, we add the forces numerically. So let's say this force has a magnitude 5 and this has a magnitude 6, then Fnet will be just 11. In the first case, because it's a right angle, I can add these by using the Pythagorean method. I will get Fnet to be equal to radical 5 squared plus 6 squared. This is radical of 25 plus 16, which is radical 41. If you calculate this, give me a second and I'll do that. You will get 6.4. Notice how when you add numerically, Fnet is way larger than when you add two vectors which don't have the same direction. Why? Because here you are adding components, and here there are parts of the forces which are canceling out. When you add numerically, here you get the largest sum of vectors. Whereas when you have opposite directions, you have the smallest sum of vectors. Since we have opposite directions and thus the forces cancel out. So when forces have the same direction, they will have the largest magnitude of Fnet and thus the largest magnitude of the acceleration. And so here our answer is C. When you have same direction, you will have the largest sum of forces and vectors in general. So now that we have defined vectors and learned how to draw them and make a force diagram for different objects in different scenarios, I'm gonna check how Fnet can give us any significance on the motion. So I have added the forces acting on the object by drawing them, or maybe later on we'll add them by numerical methods using X and Y components. We found Fnet. What can we learn from this obtained net force? What's the impact of this net force? So one particular thing I know is if all of the forces cancel out and Fnet is zero, such as the case of the book that we studied at the beginning of these slides. So I have here a book on a table, and the normal cancels out with the weight force. And we said, thus, Fnet is zero here. What's the impact of that the book will not move. Why? Because we said before as well that to have motion, you will need some forces to be exerted on the body. So if F net is 0, I will deduce that an object at rest will remain at rest. Now, if an object is already in motion, nothing will change that, and it will remain in motion with a constant velocity, essentially. This is Newton's first law of motion. We can define it as such. If the net force on an object is 0, then the object will keep constant velocity. If this velocity is 0, the object is at rest, then the object will maintain a 0 velocity and will remain at rest as well. This is Newton's first law. You can check an example of that here. We have a cart on a horizontal frictionless table. Once the cart has been given a push and released, what will happen to the cart? This cart has been given a force and then released, so the force later on does not exist. At t equals 0, there is a force, but at any time t, there is no force acting after the pushing, and the cart moves in a constant velocity. This is because F net here is going to be 0 because we don't have any forces along the horizontal direction. No forces means that this cart will obey Newton's first law, which means that no change in its motion will happen. It's already moving, so it will keep moving with a constant velocity. It will not come to stop, because if it's coming to stop, then something is pulling it to slow it down. But here I don't have any net force, no forces at all. It will not continue with constant acceleration because to accelerate, you need a force that is accelerating the object, which is not the case here. It will not continue with decreasing acceleration. There's no acceleration from the first place. There's no net force, and it will not immediately come to a stop. For any change of motion to happen, you need an F net. If there's no F net and no force, then the motion will not change. It will continue with the same speed. What would have to be done in order to have the cart continue with constant acceleration? So here, I wanted to speed up. I wanted to keep accelerating. This means that I will need F net to be non-zero. For the object to keep changing its motion, changing its speed, there should be some F net with non-zero. Let's see which of these options satisfy this condition. F net should not be 0 for the object to have a constant acceleration. If you push harder before release, well, you are releasing again, so there's no force. So again, the speed is constant. You push longer before the release. Again, once you release the cart, there's no F net anymore, so the speed will be constant. Whereas in part C, if you push continuously, then you are continuously making a net force and continuously moving, all right, with a constant acceleration. So option C is the correct choice. I have another example here, but you can take a look at it yourself. Not very important. I will proceed to our second case, which is Newton's second law. In Newton's second law, we have a net force which doesn't add up to 0. So I have multiple forces acting on the object and they don't add up to 0. So what will happen in that case? If F net is not 0, this is similar to the case which we studied before. Let me get back to it to show you. We had this ball with 3 different forces acting on it, and F net is the sum of all of these 3 forces. And we got F net to look like this. It is this vector which is pointing in an oblique direction and has this small magnitude. What's the impact of having this net force on this ball? The ball will behave through the net force acting on it. Essentially, if this ball is at rest, it will move in this direction. If the ball was not at rest, it was moving to the right, it will start tilting towards this direction. So something in the motion will change. Namely, I will say we will have some motion. The object, if it was at rest, will start moving. If it's already in motion, it will speed up, slow down, or change direction according to the scenario we have. I'll give this some math. The acceleration of the object will be directly proportional to the net force acting on it. I have a stronger net force, the object will move faster and it will accelerate faster. So the acceleration is directly proportional to the net force. F net is equal to m times a. M is the mass of the object and a is the acceleration. This equation, this is Newton's second law. This equation is a super important equation because it embeds the properties of motion in the acceleration and the causes of motion, which are the forces acting on the body. We have now a direct link between the causes of motion and characterizing the motion itself. If I have a net force acting on an object, this is the dynamics section of mechanics, we can deduce the acceleration, which is a kinematics section. And from the acceleration, I can later on find the velocity, find the displacement. So we are able to extract kinematics from dynamics. I have a net force. I can start using the net force to find kinematic properties and characterize the motion as well. Another thing I want you to see in this equation is F net is a vector and A is a vector, M is a scalar. This implies that the acceleration and F net have the same directions. So if F net is to the right, the acceleration of the object must be to the right. Also, the mass is always positive, so they can't even be opposite to each other. A and F net will always have the same direction. So in our example of the ball with three forces acting on it, F net has this direction. I can now immediately deduce that the acceleration can also be drawn to have this direction. So I know the object will accelerate in this direction, which is the same as F net. Now, because this equation is also a vector relation, I can study it in terms of x and y components as we did for vectors. So if f net equals ma, if I want to solve this numerically, I need to get rid of the vector notations, and I do that by separating directions into x, y, and z components. So I can find f net along the x direction. Its x component will be equal to the mass times the x component of the acceleration. The same thing for y components and z components. We will use these when we want to find F net numerically. Then I'm going to add the forces along the x direction and equate these to the mass times the x component of the acceleration, and so on and so forth. So with this, I can actually start with solving problems from the problem set that is associated with this chapter. My first problem is number 7. I remind you all of the problems, we take them from the Halliday physics book. So in this question, I have two forces acting on the 2 kilogram box in the overhead view of the figure, but only one is shown. So I have a block, there are two forces acting on it. I showed you just one of the two forces. F1 is, as you can see, horizontal to the right along the x direction. F2 is not shown. It is somewhere, and I'm not sure of its magnitude or its direction. We're given the magnitude of F1. This is 20 newtons. And we're given the acceleration of the object is shown here by this vector A. We're told that the acceleration has a magnitude 12 meters per second squared and is directed with an angle 30 degrees with the vertical. Pay attention, this is not with the horizontal. when I find x and y components, I use the angle with the horizontal. So this is not the angle to use. Just be careful about that. What is the question? Find the second force in unit vector notation and as a magnitude and angle relative to the x-axis. So basically, I want to find F2. How do I find F2? I'll start with the fact that I'm using Newton's second law, where F net is equal to ma, and I will apply this to our block. Namely, I'll apply it along the x and y directions, and I'll try to deduce F2 from this equation. So F net is basically the sum of F1 plus F2, right? And now I'm gonna be trying to find F2 from this equation. Remember, when we apply this equation, it's a vector relationship. I cannot add anything yet. I cannot add things numerically until I resolve these into x and y directions. Namely, I'll write f1x plus f2x equals max, and f1y plus f2y equals may. Now things look nicer, and what I will do is I'll look at the x and y components of the vectors that I know. F2, I don't know it. Actually, it's what I want. But F1, I know its x component is F1 itself because it is horizontal. F1 is horizontal, so F1x must be F1 and F1y is 0. So I'll just substitute these here. I'll have F1 plus F2x, which I don't know, equals ax. Let's look at the acceleration vector. The acceleration vector is oblique, so it will have an x component which is equal to a cosine theta and a y component which is a sine theta, where theta is the angle with the x-axis. Now, the theta I'm given here is the one with the y-axis, so I have to be careful not to use this one, and I'll name this theta prime. What is theta prime? It should be this whole angle. It's the angle with the x-axis. Or you can take this angle and put a negative sign because you measured it with respect to the negative x-axis. Either way is correct. I'll stick to the basic method. Actually, I'll use both. Let's measure this angle. This is basically 90 plus the angle theta I have here. So theta prime is basically 90 plus 30. So AX will become a cosine of 120 and AY is a sine of 120. Or measure the angle with respect to negative x-axis and associate a negative sign by hand. So I'll just look at this angle, let's name it theta double prime, and AX will be, look at AX, it is negative. So I'll put it to be minus a cosine of this angle theta prime. What is the angle theta prime? I'll look at the figure. Let me erase to keep things tidy and you can see it more clearly. So if this is theta, what is this angle? I know all of this is 90. Then this theta double prime is basically 90 minus theta, right? Theta double prime is 90 minus theta, which is equal to 60. Okay, we'll get used to measuring these angles for different scenarios in the future, and it will become, of course, way easier to you. So here I'll have AX to be minus a cosine 60. For the y component, let's look at the y component. This is also in the negative section of the y-axis. This is the positive y, and a is in the negative part. So I'll put the minus by hand, and I'll put sine 30 for the y, sine 60 for the y component. Now, my other method was to measure this big angle all the way here. To measure this angle, I put this to be 90 plus theta, which is 120. Now you will see that you will get this to be negative automatically from the calculator. Either method is correct. So when you want to find the x and y components of a vector that looks like this, either measure the angle with the positive x-axis, which is going to be a big angle, all of this, all right? Or measure this small angle, but put the minus sign by hand. That's basically what I did. So I found the x and y components of the acceleration. Now I'm just gonna plug it here. So ax is what I got here. Either I write it as a cosine 120 or minus a cosine 60. Both will really give me the same math answer. I'll write the negative one. Both are the same, no difference. For my second equation, f1y is 0, remember? So I'll have here 0 plus, what was f2y is what I want to find. I'll just leave it as it is. And I have the mass times ay, which we found to be minus a sine 60. Let's look at our equations. They are simplifying nicely. I just got that f2y is basically minus ma sine 60. And I really have all of these quantities. The box is a 2 kilogram box. The acceleration is 12. And I have sine 60 here. So this gives me minus 24 times sine 60. This is minus 21 newtons. And on the other side, in the x equation, F1 is 20 newtons. Here it is given to us. F2x is what I want. The mass is 2. The acceleration is 12. And I have cosine 60. So I can solve for F2x, which is, this is going to be none other but minus 12 minus 20, which is minus 32 newtons. So what did I find? I found the x and y components of the force. What is the question? Well, part A asks us for the second force in unit vector notation. So I'll answer part A and I'll say F2 in unit vector notation is basically F2xi plus F2yj. Remember, we represented forces in unit vectors by writing their x and y components multiplied by the unit vectors I and j. I found f2x just now. It is minus 32. So I have here minus 32i. Very nice. And for f2y, this is minus 21j. Perfect. Looks so nice. And I was able to find the force in unit vector notation. In part B, I want the magnitude of this force. Remember, we find the magnitude from x and y components using this formula, which results from the Pythagorean theorem, by the way. I put f2 to be radical f2x squared plus f2y squared. f2x is 32 and f2y is 21. I can calculate this. The minus signs don't really matter when I'm squaring. You will get 38 newtons. This is the magnitude. Part C finally wants the angle relative to the positive direction of the axis. Here I'm finding the angle from x and y components. I remind you in forces, we found the angle by using tangent theta, which is equal to F2y over F2x. Do you remember this from vectors? And I'll just substitute this. This is 21 over 32. So to find theta, I'll make tangent minus 1 of, so I'll make tangent minus 1 of 21 divided by 32. This is going to be 33 degrees. So what we did so far was we defined forces, and then we defined the impact of forces acting on a given object, the impact namely of F net, which is the net force acting on a given object. And we said if this F net is equal to 0, the object stays at rest. This is Newton's first law. And if F net is not 0, Newton's first law. And if the F net is not 0, then the object moves according to F net equal to ma, and we said this is Newton's second law. Basically, this describes everything related to the motion of objects, but we still have one more law, which is super important, and it relates the forces exerted by the two objects themselves. So we said that forces are an interaction between two objects, Earth pulling the block down, a table pushing an object up, a rope that is pulling the block across the floor, me kicking a football. So it's always two objects interacting. Newton discovered a very important a very important condition for any force exerted by any object. Any object that is, let's name that object 1, exerting a force on an object 2 will feel an opposite force exerted by object 2 on this object 1. What are we saying here? If I come and I push a block to the right by a force, let's name this the force exerted by me on the block, then will exert a force on me which is equal but opposite to the force that I exerted. I will feel a force from the block on me, and these two are perfectly equal but opposite in direction. This is Newton's third law. It says any object 1 exerting a force on object 2 will feel a negative force from object 2 on object 1. What are we saying here? 1, a single force cannot exist, and forces are always an action and a reaction. When you push the block, you feel the heaviness of the block, so you are feeling a force from the block. You push on the wall, you feel a force from the wall, and it's exactly equal to whatever push you are exerting. So one force is an action, the other is a reaction, and these two are simply just opposite to each other and equal in magnitude. This is useful in problem solving in cases where we see two objects interacting together. So notice how Newton's third law involves two objects, not just one. So here, for example, I have two skaters, and these push on each other with a force. So the thing is, when they push on each other, if one skater pushes by a force F, he will feel also a force which is equal but opposite to that. He will feel the same pushing force but in opposite direction, and they end up both moving in opposite directions, even if just one of them pushes the other. So you would see and use Newton's third law when you have two objects involved. This is another example of Newton's third law. I have here the small MCQ. A small car collides with a large truck, which experiences the greater impact force. So does the car feel a stronger force from the truck As a matter of fact, no. Both feel the same force according to Newton's third law, sorry. Newton's third law says the force by the truck on the car equals the force on the car by the truck. They just have opposite directions, so they have same length, same magnitude. They should have the same force. Now, one thing I know is the impact of these forces is going to be different. Namely, the damage to the car is more. So we can write this as a remark. This is namely because it has a smaller mass. But the forces are the same. Okay. We can solve another question here. So here, this is problem 33 from our problem set as well. I'm gonna solve this and stop here for today. This is the direct application of Newton's second law. Let's take a look at the question. I have a 3-kilogram particle, so m is 3 kilograms. Its velocity is given by v equals 8ti plus 3t squared j. At the instant, the net force on the particle has a magnitude 35 newtons. So I am given F net to be 35 newtons. What are the directions of the net force and the particle's direction of travel? So we're interested in the direction of the net force at this instant. So let's take a look at the question again. What do we have? We have the velocity is given to us and the magnitude of the net force. And we want to deduce the direction of this net force. One thing I can do is I will look for the acceleration, because from the velocity here, I can deduce an expression for the acceleration. A is equal to the derivative of v. Do you all agree? This is v prime, or the derivative of v with respect to time. Derive this equation as we did in kinematics. I'll have 8i plus 6tj. The derivative of 3t squared is 6t. I got my acceleration, which is changing with time. But we are at the instant where F net is 35. I can deduce immediately the acceleration. It will be F net over m at this particular instant, and this is 35 over 3 kilograms. I can calculate this. I will get 11.6 meters per second squared. I found the acceleration. Let's try to find at which instant this acceleration happened, because from that I can find x and y components and then deduce the direction. One thing I know in particular is direction of F net is the same as the acceleration, since F net equals ma, so these two have same directions. So I'm gonna try to find the direction of A, and this is gonna be simply the direction of F net as well. To find the direction of A, I will need to find tangent theta, which is AY over AX. Let's find AY and AX. How? I know AX is 8, perfect, from this equation, but AY is 6t. At this particular instant, I want to know what t is, and thus I can deduce AY. How am I going to do that? I'll say A is equal to radical 8 squared plus 6t all squared. And this is also equal to the magnitude of the acceleration, which I got here, 11.6. Now I'll simply solve for t. I'll square both sides. I'll get t squared is equal to 11.6 squared minus 8 squared over 36. And then t is none other but the radical of all of these. I'll calculate these. And this will be 1.4 seconds. I found this time at which the acceleration is 11.6. Now I can deduce AY. It will be 6 times 1.4. This is 8.4. Now, remember, what do I want? I want to find the direction of A from tangent theta. So now I can write tangent theta is AY over AX, and this is none other but 8.4 over 8. This is 1.05. I can deduce theta now. It is tangent minus 1 of 1.05. I'll just solve for tangent minus 1 of 1.05. This is 46 degrees. I found the angle that the acceleration makes with the x-axis, and this is the same as the angle that the net force makes, by the way, because both have the same direction. So I found the direction of the net force. Now in part B, we want the direction of the particle's travel. When I want the direction of motion, it's not necessarily the same as F net, by the way, which is a bit tricky. An object can be moving to the right, and there is an acceleration opposite to it, right? So direction of motion is not same as the acceleration. Rather, it is the same as the velocity. The object always moves along the direction of the velocity. So I'll simply find the direction of the velocity. So the angle theta that the velocity vector makes, I'll find it from tangent theta equals Vy over Vx. What is Vy? I have the velocity vector here. Its x component is 8t, its y component is a 3t squared, so I have 3t squared over 8t. This gives me, I'll substitute the time. It is 1.4 seconds. That's the instant I'm interested in. I found it in the previous part. I'll have 3t over 8. This gives me 3 times 1.4 over 8. This is equal to 0.5. And now I'll solve for the angle. I'll get 28 degrees. This is the direction of the motion, whereas the acceleration has a different direction, which is pretty common. You can simply check the case here. The velocity is to the right, the acceleration is to the left. They don't have to have the same directions.